the stability constant of a complex, you must find out these three concentrations: the concentration of the complex, concentration of the metal, and concentration of the ligand. But not arbitrary concentrations, concentration at equilibrium, because this is an equilibrium constant. Or when you say that complex has been formed, then what are the concentrations? The reaction has proceeded to large extent. Then at that point in time, when you see the complex, when you are certain that complex has been formed, you can detect complex by any technique. There is precipitation or there is color formation, which was not earlier there. For example, ligand and metal were colorless, but then complex is now colored. Solution has become suddenly colored. That indicates that complexation has taken place. Or the other thing can happen, that the metal was having a different color initially. Ligand was colorless, but then when ligand was added to the metal ion, the complex formed has a different color than the color of the metal ion which was initially there. So that these things all indicate that some interaction has happened and complex has been formed. Now our job is that at that point in time, when we are certain that complex has been formed, as is indicated by change in color or precipitation or any other physical or chemical parameter, we are certain that the complexation has taken place. At that point in time, we have to find out the concentration of the metal, which is now free metal, not the metal that we had initially added. That concentration, no, it is the concentration of the free metal ion in the equilibrium situation. Similarly, what is the concentration of the free ligand in the equilibrium situation? And then what is the concentration of the complex that has been formed at that point in time? So these three values, if you know, then you can find out the K, equilibrium constant, or the stability constant of the complex, right? So we saw yesterday that the concentration of the metal ion in the equilibrium situation, concentration of the ligand in the equilibrium situation, and concentration of the complex, all of them can be expressed in terms of Cm, which is the concentration of the ligand, which was concentration of the metal which was initially added, or Cl, concentration of the ligand which was initially added, and H positive, and some constant which is known as association constant, Ka, that the ligand has the tendency to bind itself with the metal ion as well as the hydrogen ion. We saw last time that if you are able to monitor the pH of the solution in the equilibrium situation, you can find out the stability constant. I will show those slides hurriedly again, where we expressed the concentration of the free metal ion in equilibrium, concentration of the free ligand in the equilibrium in terms of the pH, how we presented it, and then we developed an equation to find out the concentration of the metal, ligand, and the complex. Slide visible है?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So here it is. This is the concentration in which we are interested. Not this one. The concentration of the ligand and concentration of the metal in the complex in the equilibrium situation. So we are expressing the concentration of these two in terms of the pH and the CH and Cl, Cm and Cl. Cm and Cl, remember, these are the concentration of the metals and ligands which we initially added. These concentrations we know. हमें मालूम है हमने कितना मेटल डाला है सॉल्यूशन में और हमने कितना लिगेंड डाला है initially. These are expressed by Cm and Cl, and these values जो ब्रैकेट में है, these are the concentration of the metal and the ligand, free metal and free ligand in the equilibrium situation. So these are different values. So that's why we read that Cm total metal जो हमने add करा था equilibrium situation में, most of that metal has been complexed, small amount of that metal is still free, if at all it is free. So the combination of the two makes the total metal that we had added. So metal ion concentration जिसमें हम interested हैं वो है Cm minus Cm minus Ml positive. So Cm we know certainly हमने कितने moles डाले हैं per liter solution में. Ml positive, this is concentration of the complex in the equilibrium situation. This we must know, right? And then similarly the ligand concentration is again equal to HL. This is the association constant, association of the ligand. Then ultimately we express L equal the ligand concentration, free ligand concentration equal to CH. It is again the concentration of the acid we added initially minus H positive. How many H positives are there in this solution in the equilibrium solution? This is simply pH. तो ये pH मीटर आपने एक्सपेरिमेंट यही करना है कि आपने pH निकालनी है इक्विलिब्रियम सिचुएशन में, and K is the equilibrium constant which must be known before you start experiment, and the H positive is again the pH value. So M और L निकालने के लिए आपको CH और CM चाहिए, वो हमें मालूम है. H पॉजिटिव की कंसेंट्रेशन चाहिए, वो pH मीटर देगा, और Ka जो हमें मालूम होना चाहिए, और Ml पॉजिटिव. और उसके बाद हमने Ml पॉजिटिव की कंसेंट्रेशन को एक एक्सप्रेशन में डेवलप करा. दिस इज Ml पॉजिटिव, दिस इज Cl. ये हमें मालूम है कितना लिगेंड हमने शुरू में डाला है, CH कितना एसिड शुरू में आपने डाला, ये भी मालूम है. दिस इज pH वैल्यू, द हाइड्रोजन आयन कंसेंट्रेशन. नेगेटिव लॉग लेके इसको कर सकते हैं ये अपना इंटर कन्वर्शन, तो देयर इज नो प्रॉब्लम. Minus CH, again concentration of the acid we initially added. This is pH, which pH meter will give H positive concentration. This is again K and this. Once you know the Ml value, you will put that value in here also, and you will find out the concentration of the metal. So जब आपको तीनों चीजें मालूम हो, Ml की वैल्यू, कॉम्प्लेक्स की कंसेंट्रेशन, लिगेंड की कंसेंट्रेशन और मेटल की कंसेंट्रेशन इक्विलिब्रियम सिचुएशन में, ये तीनों वैल्यूज आप यहाँ प्लेस करेंगे, then you find out what is the equilibrium constant. So what do you know, what do we need to know for determining stability constant? You need to know Cm, which appears here. You need to know Cl, which appears here. You need to know CH, which appears here. You need to know hydrogen ion concentration, which will be given by the pH meter. ये वैल्यूज एडवांस में एक्सपेरिमेंट शुरू करने से पहले आपको मालूम है आपने कितना एसिड डाल दिया, आपने कितना लिगेंड डाल दिया, आपने कितना मेटल डाल दिया. And additionally, need to know what is the association constant of the H positive and the ligand. ये तीन चीजें आपको पता हो तो आप ये दो चीजें एक्सपेरिमेंटल वैल्यूज है. बाकी ये तो आप खुद ही तय करेंगे कि आपने कितने मोल्स मेटल के डालने हैं शुरू में, कितने मोल्स लिगेंड के डालने हैं और कितना एसिड डालना है. So primarily, if you know the H positive and the Ka, that is pH and the Ka, you can find out the equilibrium constant. I hope I am true. I hope I have conveyed what I need to convey. Is that okay? इसमें कोई किसी को डाउट है?
No, sir.
ठीक है. So should I proceed now? I will go to the second part. How spectrophotometer can be used to determine the equilibrium constant. So, as I said yesterday, optical properties of a complex are governed by the formation of coordinate bonds. Once bond is formed, complexation takes place, color of the compound changes, whole geometry changes, the ligand, the metal which was earlier in the ionic form in this solution are at the best loosely bound with the solvent molecules and form a complex, what we call aqua complex. Now that metal ion is engaged in the bond formation with a ligand, which most of the time, as I said, is an organic molecule, has an organic framework, and many times it is a chelate complex also. So it is a definite geometry, and the compound has different color. So because of that splitting of the d orbitals, and it has unpaired electrons, then it becomes colored, and once it is colored, you can use spectrophotometer for various purposes. One of the aim is to determine the stability of the complex. Not only stability of the complex, you can investigate what is the stoichiometry of the complex, what is the composition of the complex. I mean, how many ligands have attached to the metal ion, or is it a 1:1 complex, one metal ion and one ligand, or two ligands have attached to this one metal ion, or three ligands have attached to the one metal ion, or four have attached, or five ligands have attached to one metal ion. What is the stoichiometry of the complex? What is the composition of the complex? Or in other words, how many water molecules have been displaced by ligands? If all water molecules have been displaced by an unidentate ligand, then it is 1:6. Stoichiometry is 1:6. If it's a bidentate ligand, if only one ligand, if it's a monodentate ligand, but then all water molecules have not been displaced, only one ligand has been displaced, then it is 1:1 reaction. Then complex is M water 5 times retain their positions, only one ligand L enters and one water molecule goes out. So it depends upon situation, it depends upon the concentration of the ligand, it depends on the affinity of the ligand with the complex, etc. These are reaction conditions. So you can investigate, we will see how spectrophotometer can be used to determine the stoichiometry or composition of the complex along with the stability of the complex. We can, and for stability, I will say again, the pathway to determine the stability of the complex is that you should be able to determine three concentrations in the equilibrium situation: concentration of the complex in the equilibrium situation, and concentration of the free metal in the equilibrium situation, and concentration of the free ligand which has not been complex in the equilibrium situation. If you know these three things, concentrations, you put them in the equation, you can find out the equilibrium constant. There is no problem, right? So the key is how to find out the concentration of these three species. What are the three species? Complex, then free ligand, and free metal ion. Okay? Is that okay? Now, the functioning of a spectrophotometer is based on a law which we call Beer-Lambert law or Lambert-Beer law, which says that the absorbance, that is the amount of light which is absorbed, the number of photons which are absorbed by the analyte, by the absorbing species, is dependent on three things. Number one, the concentration, how many molecules are there in the solution to absorb the photon. So larger the number of molecules, higher the concentration, larger will be the absorption, lesser the concentration, lesser will be the absorption. So this is straightway a simple argument that the number of absorbing molecules which are responsible for the absorption of the photon will increase the absorption, and if the solution is dilute, then absorption will be less, right? So second thing is, what is the path length of the photon? What is the width of that solution, the vessel which is holding the solution? And because for all spectrophotometers, the width is 1 centimeter, the size of that qubit is 1 centimeter. So for all practical reasons, this remains constant. The path length remains constant for all experiments. So L is a constant, it is 1 centimeter. And then third thing, very important, is that according to the first two things, you can increase or decrease the absorption by increasing or decreasing the concentration, and also by increasing or decreasing the path length. If If you increase the path length, the absorbance will increase. If you decrease the path length, absorbance will decrease. Similarly, if you increase the concentration, absorbance will increase. If you decrease the concentration, absorbance will decrease. There is absorbance is directly proportional to concentration. It is also directly proportional to the path length. The third thing is that that if you have two substances having same concentration, you suppose you have a copper sulfate solution and you have nickel sulfate solution. Both solutions have same concentration, 1 mole per liter for copper sulfate and 1 mole per liter nickel nitrate solution, for example, and you place them in this same cuvette having same path length. Still absorbance is different in the two situations. So there is something which is changing this the absorbance, because concentration and path length are same in both cases. So that is the third thing, is nature of the substance. So some substances have they're quite strong absorbers of the radiation, and some are weak absorbers. Or technically, the third thing can be written as some in some situations the transition. This is after all, what's happening during this absorption process? The molecule is going from ground state to the excited state. Who is absorbing this photon? It's the electron, which goes from one energy level to the electronic energy level, I must say, to the another electronic energy level. These electronic energy levels may be atomic orbitals, or they can be molecular orbitals, depending upon the situation, right? So, for example, in the organic dyes, you have diazo compounds. They are strong absorbers, highly colored compounds, nitro compounds, जैसे आपकी मेहंदी वगैरह है. These are strongly, absorbing materials. That's why they are dark colored. These are organic compounds, the nitro compounds, or lipsticks, etc. So they need the substance, absorbing substance may be an organic molecule or an inorganic molecule or a metal ion, depending upon the situation. So the energy levels may be atomic orbitals or molecular orbitals. And who is absorbing these photons? It is the electron which is absorbing these photons and going from one energy level to the energy level. The amount of energy that photons gives must match with the energy difference between the two energy levels. So all transitions are not allowed fully. Some transitions are fully allowed, that even if the photon has absolutely same energy required for transition from one energy level 1 to 2, the molecule may not absorb happily the radiation, because the transition is forbidden. Such substances which do not happily absorb radiation, even if the proper radiation is given, then they are poor absorbers. And some substances which absorb efficiently the photon, they are known as strong absorbers. So strong absorbers are highly colored, deeply colored, and weak absorbers are dull colored. So you have zinc compounds, or nickel or for that matter these iron compounds. Many of the salts are faintly colored, but some salts are intensely colored. Say camphor is intensely colored. If you drop one crystal of camphor in a glass of water, it becomes deeply colored. So that's the fundamental difference, that the camphor is strongly, deeply colored. So this tendency, this effectiveness, or this effect that some substances are quite strong absorbers of radiation and some are poor absorbers of radiation. In other words, in some situations, transition is highly probable, is allowed, and in some situation, electronic transition is not probable, or it is not allowed. This is measured in a physical parameter by a parameter known as molar extension coefficient. So what is molar extension coefficient? If you have concentration from this equation, if you have C equal to 1 mole per liter and L is equal to 1 centimeter, so then A becomes equal to molar extension coefficient. So how can I define molar extension coefficient? It is the absorbance when the concentration of the absorbing material is 1 mole per liter and path length is 1 centimeter. So it depends upon the nature of the substance or to what extent that transition is allowed. If transition is not allowed, then molar extension coefficient is small. So numeric, if I give you two substances, I say that this compound has molar extension coefficient 10 or 20, other one has 500. So obviously it must give you the idea that compound which has molar extension coefficient 500 is a strong, better absorber, and its more, its transition is allowed, whereas the other compound which has molar extension coefficient just 5 or 10 is a weak absorber, will be dull in color. It will be faintly colored. It will not be strongly colored, right? So that's known as molar extension coefficient. And then the first thing that we do is determination of the lambda max. So lambda max occurs, the absorbance occurs at the lambda max, and molar extension can be determined at the lambda. The first step is you identify the lambda max. And how you identify the lambda max? You place solution of any concentration. You need not to measure the concentration. Prepare solution of a compound whose lambda max you want to find out. Prepare its solution without weighing it. Just put it in this proper solvent, dissolve it, and place it in the spectrophotometer, and give a command to the spectrophotometer to scan all wavelengths, right from say you want to find out lambda max in the visible region. Your compound is already colored, so you know for certain that it's absorbing in the visible region. That's why it is colored. Had it not been absorbing in the visible region, it would be colorless. So you give a command that can send all wavelengths from 400 to 800 nanometer through the solution, and the computer will display a graph that it has maximum absorbance at this particular wavelength. So that becomes the wavelength, that becomes the lambda max. Now you make another solution of the same substance where you know the concentration of the solution. Prepare a solution of the same material, same substance, where you know what is the concentration. That is, you weigh it first and then dissolve it in known amount of the water. That's not how you know the concentration. You know the amount of the salt or the compound you have taken, and you know the volume of the solvent in which you have added it. So you know the volume, you know the amount. That's how you know the concentration. And put it again in the spectrophotometer. Now fix the wavelength. You have identified the lambda max. Fix the wavelength and find out the absorbance. Once you find out the absorbance, you place it here. Absorbance you know now. Concentration also you know, because you have prepared a solution where you know the volume of the solvent, you know the amount of that you have added, and you know the L. So you divide A by Cl, you will find out the molar extension coefficient. Molar extension coefficient depends upon nature of the substance. It is independent upon the concentration. Independent of the concentration. So you prepare different solutions with different concentrations, molar extension coefficient will remain same, because it is the absorbance per unit concentration per unit path length. It is A by Cl, right? So that's how we determine two things beforehand. Number one, you determine lambda max first, and then you determine molar extension coefficients. Once you are with these two parameters, you can do anything with that compound now. If you know the lambda max, you know half of the journey is done, half of the solution is done, right? And then secondly, you must know the lambda max, the Emax. Emax is molar extension coefficient. So how you find out molar extension coefficient? You prepare a solution of the substance with known concentration, and then you put that solution into spectrophotometer, fix the lambda max value, and then record the absorbance, and then divide that absorbance by the Cl. You find out the molar extension coefficient. What are the units of the molar extension coefficient? As you know, the absorbance is unitless because it is the ratio of the intensities log I0 by I. So it's unitless. However, the molar extension coefficient is not unitless. It is having the unit of concentration inverse and centimeter inverse. So it is 1 by Cl. So write concentration units are moles per liter. So I can write liters per mole per centimeter, because it is 1 by concentration into L. So A by CL. So the concentration units are moles per liter. So it becomes reciprocal, becomes liters per mole, and centimeter inverse, because centimeter is the unit of the length, right? So let's come to the complex formation. So you have a simple form, M plus L giving ML is the equilibrium constant, or call it stability constant. It's again given like this in the simple situation. Cm and Cl are molar concentrations of the metals and ligand that you have added at the start, not at the equilibrium. At the start, you have added 2 moles of the ligand and 2 moles of the metal. So Cm is equal to that, the concentration of the metal that you initially added is equal to concentration of the metal in the equilibrium, free metal in the equilibrium situation plus complex. Similarly, concentration of the ligand that you initially added is equal to concentration of the free ligand in the complex in the equilibrium situation plus Ml complex. So absorbance of Ml, you can find out absorbance of the Ml. That how you will find out? First, place the solution, the complex solution into the qubit, and give the command for finding out, scanning the lambda max, right? And send all wavelengths from 400 to 800 through the qubit and find out absorbance wavelength at which maximum absorbance occurs. So you find out lambda max. Second time, you take this complex solution and you record its absorbance. So the concentration is equal to absorbance by molar extension coefficient into cell. So before for finding this concentration of the complex, you must know the molar extension coefficient. That you have to prepare a solution of known concentration of the complex and to find out its absorbance, and divide it by molar extension coefficient, divided by C and L, and you'll find out the molar extension coefficient. So once you have the molar extension coefficient, you can find out the concentration of the complex in any situation. So free metal ion concentration is Cm from this equation, Cm minus Ml. If you know the Ml is A by molar extension coefficient into L. Similarly, concentration of ligand is Cl minus A by molar extension coefficient into L. So you have 3 things. Ml is itself A by molar extension coefficient into L. M is concentration is also known, L concentration. You put these values here and you find out the stability constant. No problem. There is no problem. You find out the concentration of Ml, you find out concentration of M, concentration of L, you put them here and you find out Cm and Cl are the initial concentrations that you added to the solution. There is no problem in finding out, in knowing that. The only thing is that you know the absorbance, that is the value that will be given by the spectrophotometer, and molar extension coefficient you must know beforehand for that particular complex, and then multiply with path length, which is usually 1, to its width is 1 centimeter, find out the equilibrium constant. Now, let's take an example of iron 3. Say you are using ferric sulfate or ferric chloride solution, add sodium thiocyanate solution to it, and you have a complex formation like this, blood red color. This test you must have done in your graduation classes, confirmation test for iron 3. So you take the salt solution, you add concentrated nitric acid, little bit of nitric acid, so that iron gets converted from +2 to +3. Then you neutralize the acid, and then you add potassium thiocyanate. Blood red coloration immediately is formed. Then you say that iron 3 is confirmed. The complex that is formed during this process is that one water molecule, actually this must be written as Fe3 aqueous. Fe3 aqueous means 6 water molecules are loosely bound to the iron 3 plus, only one water molecule goes away and thiocyanate comes in. 5 water molecules are still intact. So this is penta-aqua thiocyanate 3 plus. So iron 3. So blood red color. Lambda max of this complex is 450. Find out the value of lambda max first. Find out the Emax also. Once you know these two values, find out the absorbance at 450 of a solution of iron 3 in excess of the thiocyanate, so that all iron is complexed. You must add an excess of thiocyanate so that you are sure that all the iron is complex. Now measure the concentration of this complex from A by Cl. What is the absorbance and what is the molar extension coefficient into L? Iron 3 and this thiocyanate are colorless, and the complex is blood red in color. So put those values here and you find out the equilibrium constant, right? So now there are the method which is by name mentioned in the syllabus, which is known as Jobs method. This method is used to determine not only the stability constant of the complexes, but also the composition of the complexes. So, कोई जवाब नहीं आया चरण जी, लिगेंड कोई मेल के जवाब नहीं आया। अब क्या करें, नहीं ये फर्स्ट एक्सपेरिमेंटली करेंगे, यही किसी कॉम्प्लेक्स को लेके ये स्पेक्ट्रोफोटोमीटर को यूज करके आप कंपोजिशन और निकाल सकें किसी कॉम्प्लेक्स की। तो बेसिक प्रिंसिपल क्या है इस मेथड का कि हम दो सॉल्यूशंस बनाते हैं, एक मेटल का और एक लिगेंड का सॉल्यूशन अलग अलग क्लास में। सिर्फ कंडीशन ये है इस मेथड की कि दोनों की कंसंट्रेशन सेम होनी चाहिए, यानी अगर एक 0.1 मोलर सॉल्यूशन है लिगेंड की सॉल्यूशन, तो कॉम्प्लेक्स की सॉल्यूशन भी 0.1 मोलर ही होनी चाहिए। तो इक्विमोलर सॉल्यूशन बना के फिर उनसे 5-10 सॉल्यूशंस बनाते हैं उनसे। एक सेकेंड, एक सेकेंड। हेलो, साहब वो टेबल अब ज्यादा डैमेज है, मैंने पिक्चर भेजी वो सारा ही टूटा हुआ है। जो नया वाला टेबल है ना वो पहले से ज्यादा डैमेज है, उसके बिल्कुल ही परखे टूटे हुए हैं। हेलो, तो बेसिक प्रोमाइस इस मेथड का ये है कि हमने दो सॉल्यूशंस बनानी है, इक्विमोलर सॉल्यूशन बनानी है, एक लिगेंड की और एक मेटल की। फिर उन दोनों में से उन दोनों को मिक्स करना है, लेकिन मिक्स अपनी मर्जी से नहीं करना है, इस तरह से मिक्स करना है कि टोटल कंसंट्रेशन दोनों की सेम रहे, जो भी मिक्सचर बनाए। मतलब सपोज मैंने 1 मोलर सॉल्यूशन यानी 10⁻⁻² मोलर सॉल्यूशन दोनों की बनाई, तो फिर मैं टेस्ट ट्यूब ले देता हूं 10। एक पहली टेस्ट ट्यूब में 1 मिलीलीटर डालता हूं मेटल का सॉल्यूशन और 9 मिलीलीटर डालता हूं लिगेंड का सॉल्यूशन, टोटल वॉल्यूम 10 रखता हूं। दूसरी टेस्ट ट्यूब में 2 मिलीलीटर मेटल का और 8 लिगेंड का, तीसरी में 3 7, चौथी में 4 6, पांचवी में 5 5, फिर 6 5, फिर 7 3, 6 4, 7 3, फिर 8 2 और फिर 9 1 और फिर 10 0, इधर से भी 10 0 ले लो। ये 10 या 12 टेस्ट ट्यूब्स बनेगी जिसमें टोटल वॉल्यूम सबका सेम है, टोटल कंसंट्रेशन दोनों का मिला के सब दोनों का सेम है, लेकिन डिफरेंट प्रोपोर्शन में हमने मेटल और लिगेंड मिक्स किए हैं। और फिर हम इन सभी क्या नाम है टेस्ट ट्यूब्स का एब्जॉर्बेंस नोट करेंगे। और सबसे ज्यादा बेसिक प्रिंसिपल मेथड का ये है कि हाईएस्ट एब्जॉर्बेंस उस सॉल्यूशन की होगी जिसमें मेटल और लिगेंड उसी रेशो में हूं जिस रेशो में वो कॉम्प्लेक्स में है। मतलब कॉम्प्लेक्स की जो स्टाइकोमेट्री है, अगर कॉम्प्लेक्स की स्टाइकोमेट्री ये है कि उसमें एक मेटल के साथ 4 लिगेंड लग रहे हैं, तो उसी ट्यूब की हाईएस्ट एब्जॉर्बेंस होगी जिसमें मेटल और लिगेंड इसी रेशो में हो, 1:4 में हो, जिसमें जो स्टाइकोमेट्री जो रेशो मेटल की स्टाइकोमेट्री कॉम्प्लेक्स की स्टाइकोमेट्री में है। दिस इज द बेसिक प्रीमाइस ऑफ द मेथड। मैं आपको एक टेबल बताता हूं जिसमें मैंने एक डेवलप किया है। ये देखिए, ये मैंने 2 सॉल्यूशन बनाए मेटल और लिगेंड के, 10⁻⁻² मोलर सॉल्यूशन, राइट। तो यूजुअली डाइल्यूट सॉल्यूशन लेते हैं क्योंकि स्ट्रॉन्ग सॉल्यूशन की एब्जॉर्बेंस बहुत ज्यादा होती है और बेयर-लैम्बर्ट लॉ जो है कंसेंट बहुत डार्क ये अपना सॉल्यूशन हो, कंसंट्रेशन हाई हो तो बेयर-लैम्बर्ट लॉ डिविएट करता है। बेयर-लैम्बर्ट लॉ बेस्ट ये ओबे होता है सॉल्यूशन थोड़ी डाइल्यूट ही हो, इसलिए मैंने 10⁻² लिख दिया यहाँ पे। तो पहली ट्यूब में मेटल की वॉल्यूम मैंने 0 डाल दिया, तो इसमें 10 का 10 पड़ गया। ओहो, या हाँ, तो मेटल की ये कंसंट्रेशन है, थोड़ा गंदा लिखा है मैंने, ये वॉल्यूम है और ये कंसंट्रेशन है, ये लिगेंड का वॉल्यूम है और लिगेंड की कंसंट्रेशन, और ये टोटल कंसंट्रेशन, ये टोटल कंसंट्रेशन। सो पहली ट्यूब में मेटल मैंने बिल्कुल डाला ही नहीं, तो मेटल की कंसंट्रेशन 0 है। लिगेंड मैंने डाला 10 मिलीलीटर, क्योंकि टोटल वॉल्यूम मैंने सेम रखना था, तो लिगेंड की कंसंट्रेशन आ गई 10 डिवाइड बाय 10 का मतलब है वॉल्यूम टोटल 10 है इंटू 10⁻²। सो 10 और 10 कट गया, तो ये रह गई लिगेंड की कंसंट्रेशन 10⁻²। अब देखिए सेकंड ट्यूब में मैंने मेटल लिया 1 मिलीलीटर और कंसंट्रेशन मेटल की आ गई 1 डिवाइड बाय टोटल वॉल्यूम ऑफ मेटल डिवाइड मेटल सॉल्यूशन डिवाइड बाय टोटल वॉल्यूम 1/10 इंटू 10⁻², ये बन गया 10⁻³ मोलर। डाइल्यूट हो गया, मेटल की कंसंट्रेशन कम, राइट। और लिगेंड लिया मैंने 9, सो दिस बिकम्स 9/10 इंटू 10⁻², ये 9 इंटू 10⁻³ है। अगर आप यहाँ पहली ट्यूब में टोटल कंसंट्रेशन देखोगे, एक की 0 है और दूसरी की 10⁻² है, तो 10⁻² ही रही। सेकंड वाले में एक कंसंट्रेशन है 10⁻³ दूसरी है 9 इंटू 10⁻³ ऐड कर दीजिए दोनों को, 9 इंटू ये 9 और कॉमन रहेगा, ये 1 प्लस ये 1 हो गया, ये 10⁻², 9 और 1 10 हो गया, तो ये दोबारा नहीं, हाँ, ये 10⁻³ है और ये 9 इंटू 10⁻³ है, तो 10⁻³ कॉमन आएगा, इसका 1 आएगा प्लस 9, 1 प्लस 9 10, ये दोबारा 10⁻² आ जाएगा। थर्ड ट्यूब में मैंने 3 मिलीलीटर मेटल लिया, 3/10 इंटू 10⁻³ और ये मैंने गलत लिख दिया, 10⁻² है ये कंसंट्रेशन, सो दिस बिकम्स 3 इंटू 10⁻³ दिस इज 10⁻³ हियर, ये मैंने गलत लिखा। तो मेरी स्लाइड्स को मतलब मैं गलती भी करता हूँ, ऐसे नहीं नोट करते रहना और फिर यही जवाब मुझे लिख दो, ठीक है। दिस इज 7/10, अब मैंने जल्दी में लिख दिया, यहाँ पे लिखना था मुझे 7/10 इंटू 10⁻², वो आएगा 7 इंटू 10⁻³। तो यहाँ पे जब ऐड करेंगे 10⁻³ है, ये कॉमन आएगा 7 प्लस 3 10 आएगा, तो टोटल कंसंट्रेशन 10⁻² आ जाएगा। इसी तरह हर एक ट्यूब में मैंने फिर मेटल बढ़ाता गया, लास्ट वाली ट्यूब में टोटल 10 मिलीलीटर मेटल पड़ेगा सॉल्यूशन और लिगेंड 0। यहाँ पे मेटल की यानी ये प्योर मेटल है और फर्स्ट वाली ट्यूब में प्योर लिगेंड है, तो इसमें एब्जॉर्बेंस दोनों में 0 आएगा, क्योंकि एब्जॉर्ब कर रहा है कॉम्प्लेक्स, तो दोनों में कॉम्प्लेक्स बनने का कोई चांस नहीं है, बिकॉज फर्स्ट वाली ट्यूब में मेटल है ही नहीं, तब भी कॉम्प्लेक्स नहीं बनेगा, और सेकंड वाली लास्ट वाली ट्यूब में लिगेंड है ही नहीं, तो तब भी कॉम्प्लेक्स नहीं बनेगा। अब मैं थक गया बोल बोल के, अब आज इतना ही, कल हम इसको कंप्लीट करेंगे क्योंकि आज पूरा होगा नहीं, तो अभी मैं